All right, so this is the autonomous rover project. My name is Jose Reyes and I'm a mechanical engineering major.
I'm Brian Beaver. I'm an electrical engineering major. I'm Jacob Schaefer and I'm a computer science major. So the initial problem that kind of motivated this entire project is freshman group members had COVID-19, and per campus policy, he was isolated for quite a while. And during that time, staff members had to bring food. And we felt that that was kind of both a waste of time for those staff members and also not exactly ideal, considering that they would have to walk from the Loom over to the Benedictine Center, no matter the conditions. I'm thinking mainly of some of the snowstorms we got that year. So the motivation primarily was to create a drone that could then deliver food autonomously for the staff members to students in quarantine. It would have other objectives like being able to deliver goods and services to people in cities and across campuses.
So some of the mechanical requirements for this vehicle, as most of you may know, the University of Umary has multiple different terrains, such as gravel, pavement, tile, carpet, and also lots of inclines that people have to walk over. The rover would need to be able to traverse and navigate through campus over all of these said terrains. And so I broke down the mechanical concepts into three main categories: the steering, the speed control, and the suspension. First, we're going to go with this. We're going to talk about the steering. So for the steering, this is all based off of Ackerman steering. The goal of Ackerman steering is to have a common turning radius point, which is perpendicular to the vehicle, where each independent wheel has its own turning radius that is perpendicular to the wheel pointing towards the turning radius. If this is confusing, I have a picture here showing this turning radius and each respective individual wheel's turning radius that is perpendicular to the wheel angle. So I ran a quick simulation of moving the turning radius from the left to the right. Theoretically, we should be able to get a 0-point turning radius, meaning the car is able to stop in place and turn without having to traverse any obstacles. As far as the velocity controls go, we wanted to control the centripetal acceleration that the rover was going to embark on when going on sharper turns. You may know this, that when you're driving and you're about to take a really sharp turn, you're of course not going to go 50 right into a sharp right turn. You're going to slow down and then take the turn accordingly. We took that same approach where we had a set centripetal acceleration that we wanted to maintain. We would pick one of the outer wheels of the turn as a reference for the maximum velocity, as that wheel will experience the highest velocity around the turning point. And then from there, we use a ratio of that reference velocity to determine each other wheel's motor velocity in order to maintain a constant angular velocity for each wheel around the turning point. And here's just a quick simulation that we did. As you can see in this right figure, as you did in the green line in our controlled environment for the velocity, as you increase the turning radius past the centripetal acceleration threshold, the velocity of the motors decreases as you decrease the turning radius. And lastly, this rocker bogie suspension mechanism. We got this suspension idea from the NASA Mars Curiosity rover. The advantage to this is to use small shock absorbers and springs like traditional RC cars, as some of us have tried that in the past in other projects, and it did not go exactly as planned. This eliminates that problem, as we can use larger pieces and different materials in order to have more reliability and durability. This works by having the middle axis and front axis of the vehicle pivoting around a free moving bogie joint, and then the bogie joint and the rear axle moving around a free moving rocker joint, which is connected to the main body of the vehicle, which will house most of our electronics. Here's a quick just slide showing the derivations to calculate the positioning of the body when the car is moving based off of an input to each individual wheel. The main concept here is to show that we know that each wheel, no matter the variability of the input from the ground, that each of the 6 wheels will have constant traction with the ground beneath it.
As far as the electrical technical details, we had to take all the mechanical concepts and kind of bring them to life. So the 4-wheel steering system, we needed 4 servos to control each of those, as well as DC motors and motor drivers to control the 6 wheels that are in contact with the ground. And they needed to be capable of high amperage motors for the necessary torque, and then also high voltage resolution so we could control the speed accurately. We also needed sensors for the obstacle detection, so it couldn't run into anything. So they had to be able to detect angles or detect obstacles at a distance from multiple directions as well. As far as the microcontroller, it had to have certain functions as well. So it had to have PWM modulation capabilities for the motor drivers and servo motors, various timers to process the sensor data, a low power mode also for sleep functions. So when it wasn't being used, it could go into a sleep mode to conserve energy, as well as many GPIO pins for the various controls and all the components. So you're good. So first I had to develop a kind of a 5-volt regulator circuit for the different sensors that ran off 5 volts, as well as the servo motors, which ran off of that. With a battery at 12 volts, it would fry those components. So a 5-volt regulator circuit was needed. So I used the LM7 voltage regulator, which was capable of 1.5 amps for the servos and the ultrasonic sensors. And then there was a small capacitor that was put in that circuit as well to control voltage spikes from the servo motors and all that. As far as the battery goes, it had to be capable of outputting the proper amperage for when the motors need to turn or when there's a load, as well as for when the servos all steer at the same time. It had to also be long lasting, so it could make a trip across campus if needed, and possibly a couple trips before needing a charge. And then a voltage that worked well with the motors.
So on the software side of things, I had to develop a pathfinding algorithm to allow this drone to navigate by itself without any human intervention. We had a couple ideas at the start about how we were going to do this, and we kind of narrowed it down to using ultrasonic sensors and a GPS tracker. And the algorithm took the form of an obstacle tracing method, as opposed to something like the Dijkstra method, which essentially tries to predict the shortest possible route to the end destination before the drone even leaves its starting place. So the obstacle tracing method instead just tries to navigate the drone as quickly as possible to the end destination and deals with objects as they present themselves in its path. So here are a couple code snippets of how that how I simulated on a computer, just to kind of prove the concept that the pathfinding algorithm will work. This specific method for obstacles around the drone, how it works is it takes in the current coordinates of the drone along with the coordinates of the obstacles in the simulation, and through the use of just some simple geometry, it outputs whether the drone is less than 2 away. 2 in this case is just an abstract distance from the drone to the obstacle. This next little code snippet is how it navigates around an obstacle. Unfortunately, we weren't able to implement this in the final design due to not having a GPS tracker. However, how this works is it takes in the drone's current coordinates as well as its final destination coordinates, and it's the magnitude of those coordinates, and then flips them so that way it creates a perpendicular vector to its end destination, and it will travel in that direction for as long as it needs to until it can tell that it's away from any objects in its path. At that point, it will resume standard travel towards the end destination. Here's a video of that simulation. So you can see it moves away from the object and then proceeds to travel to the right until it's free of the object, and then begins to move back down towards the end destination. And a moment here, it'll consider itself having reached the end destination. So again, unfortunately, we weren't able to implement the GPS in the final prototype, just due to some constraints with actually getting a functional GPS tracker working hardware-wise. However, we were able to implement ultrasonic sensors. This is a little code snippet of how that works, which basically, when the code tells the sensors to fire, it will raise a trigger pin to high, as well as starting a timer before lowering that trigger pin. The sensor will see that that trigger pin went high, send out a ultrasonic pulse from its echo pin, and all the while that timer is continuously counting up, leaves the pulse back. It'll then calculate how long that pulse lasted for by taking that the initial time when the pulse was sent out and the time when the pulse arrived back at the sensor. And using that, we can calculate the distance the drone is from any object in front, to the side, below, and to the sides. Finally, in order to actually get that pathfinding to work, we send those distances into a function that will navigate around an object. How that works is it checks those distances against some predetermined values that we consider acceptable tolerances. In this case, our minimum distance to an object in front is 12 inches. So in 12 inches, it needs to navigate away from that object. Once it checks those distances and sets a series of Booleans, it will then send those through a series of if statements to determine what is the correct direction it can turn. This only has the if statement for whether it can turn right or not. There is a series of other ones that will determine whether it can, if it can't turn right, can it turn left? If it can't turn left, can it back up?
All right, so moving on to our initial design or our prototype, it's located right over there. The CAD you see on the screen, the only components that are missing is the PVC pipes that are installed in between the casings for the motors and the ball bearings that we used. The reason why we chose 3D printed casing and PVC pipe from assembling and framing most of this vehicle is due to and its availability here at the school and at different retailers in town. We chose to go with a gear differential instead of the linkage differential that the actual NASA Curiosity rover uses. This is because the gear differential at this scale is a lot more reliable due to the linkage differential having a lot more moving parts. This vehicle has front and rear wheel steering, with each wheel having its own servo motor in the front and rear axles. And then each individual of the 6 wheels has its own DC motor attached to it to avoid having to use a differential in each axle, and so that we can more accurately control each wheel speed to reduce tire slippage. Here's a quick video showing the differential in action. It's upside down right now as it needs to help maintain the base of the electrical components. And then here's just a quick side-by-side of our derivation-based simulation. So based on the calculations that I showed you earlier, this is the inputs that we, or this is the output we got from the inputs from the ground that we simulated. And then on the right is the our prototype without any of the electrical components installed, basically showing that all 6 wheels can stay on the ground, giving varying inputs to the rover.
As far as the electrical initial designs, we had 6 DC motors at 550 RPMs. Those motors gave us a good amount of needed, and then also had a good range of speed, so we could turn slow when it was turning and go fast on straightaways. And then controlling those was the 4 motor drivers. They were capable of high amperage. And then we had the 4 servo motors, which had were capable of high torque turning as well and featured metal gears so there wasn't as much wear. Controllable up to 180 degrees so we could get our steering angles. And those were PWM controlled. And then our HC-SR04 ultrasonic sensors for the obstacle detection. For the microcontroller, we used the STM32F446. It had all the GPIO pins we needed, as well as timers for use with PWM. On the bottom picture there is just an example of different PWM signals. So those were used to control the motor drivers as well as the servos. It featured a low power mode, high CPU clock to process the pathfinding algorithm, and also allowed us to use FreeRTOS, which is a real-time operating system. So pathfinding and motor control and servo control could happen basically simultaneously.
For the initial design of the software, this is just a quick pseudocode overview of what our initial hopes were, including structures to define coordinates that we would receive from a GPS tracker, function to calculate distance to objects, as well as navigating around them and detecting them. Along with this, we would have a function that would essentially act as standard navigation that would try to get the drone as fast as possible, regardless of the obstacles in its path. And all that ends with just a main function that just sets everything up.
All right, and then here's a quick video going over the physical testing. As you can see, this actually mimics the simulation I showed earlier, where the turning radius is moving from one side of the rover to the other. Where you just saw that there was a 0-point turn radius that we are able to hit. The next clips are going to be showing the rover going over various terrains. And as you can see here, as it goes over this little ramp, it is able to maintain constant contact with the ground in all 6 wheels. Here's the rover going over rocks. On an inclined pavement, tile. We did not get it to work on grass, but we believe that this was due to the height of the wheels and the fact that we did not have actual treads on the rover. And then here's a quick demonstration of the ability for the turning radius of the vehicle to accurately hit a 0-point turn. This clip is showing the turning radius getting smaller and smaller, and then the turning radius will flip to the other side of the rover and eventually work back out to a straight line. Okay, then here's just a brief overview of our final design. Changes that were made were rubber injection molded wheels with treads and also increasing the wheel diameter. And then also changing the 3D printed parts with aluminum casing, as well as improved geometry from the PVC. And then also here's just an overall brief look at the cost for the Rover, which is a little under $700, not including electrical components. The manufacturing time would be very similar to the prototype, as machining the aluminum would take up very similar time frame as the 3D printed parts that were needed for assembly.
Thank you very much.